Okay, so in the previous class, we ended up with the unity feedback block diagram. What happened? Unity feedback block diagram, and here we had the plant only, not controller anymore at this stage. And we assume that the sensor is ideal, so there is no sensor transfer function here, so that's why unity feedback. Desirable input to the system in frequency domain and the real output of the system. And this is the sum operator as I showed you in the Simulink. And we saw that, and we derived together that closed loop transfer function is defined as output over desirable input. This is definition. For unity feedback is G1 plus G. And if I name it as B, and this is the error signal, obviously. Open loop transfer function we defined, transfer function, not transfer B. We defined, right? Transfer function, open loop, was B over E, right? So this is closed loop transfer function. These are definitions of linear control systems. So also we saw from this sum operator that the error signal is plus X minus B, but because this is unity feedback, B is exactly this Y, so X minus Y. And our intention in control, as I'm going to show you throughout the semester, is to make a steady state error signal to 0. Okay. So if you find Y from here, Y is xg 1 plus g, and implement it here into error signal. So the error signal becomes x minus xg 1 plus g. So this is x 1 plus g minus xg divided by 1 plus g. And this gives you this, with this term goes to New York, and you get error signal in S domain gonna be X input, desirable input. Desirable input can be the speed of your car in the cruise system, can be desirable temperature of the room, can be the desirable angle of the robot, can be desirable altitude in the space shuttle, can be whatever. Okay, 1 plus open loop transfer function. G is open loop transfer function. Here we go. Why I'm defining that? Because now I want to teach you this topic. Final value theory. Final value theory. What does it say? It says if you have a Laplace of any function, f of t at steady state value at the time domain of this, if I provide this here, okay, gonna be a limit of s f of s when s goes to 0. This is final value theorem or theory here. Okay, you're gonna tell me why payment s goes to 0, you get a steady state, mean t goes to infinity. This ss is not German one. This is steady state. Steady state means after settling. As you're gonna see in this course, or maybe you have seen in the vibration course or ME430 course, if this is the desirable input, you have this kind of profile, and this is steady state after settling. Okay, when time goes to a large number, to a certain number. When I say when s goes to 0, t goes to infinity, because I define you from the fundamental of Laplace, s is j omega. Omega is frequency. When I say s goes to 0, means there is frequency 0. Means there is no oscillation anymore, not transient. We can make an analogy like this. So it's steady state in time. You got it, everyone? I just want to take the leverage of this and use that for our lovely error signal. Here we go. Okay. It says ESS, steady state error signal. I'm going to show also today in the Simulink. Okay. Means when t goes to infinity is a limit of s, e of s. Here we go. When s goes to 0. So what is e of s? We have it as desirable input 1 plus open loop transfer function of your system, robot, room, whatever. Here we go. Okay. Let me go to example of that. Can I go to next page? Yes, guys?
Professor?
Yes. We derived the previous class. You were not, you were absent? Yeah, yeah. So please look at it. Please, because if you don't understand this, you don't understand the rest of the semester, okay? Good for asking, okay? So, now, suppose that I give you the closed loop transfer function of this example, s squared plus 1. Does this remind you any system from the beginning of this semester? Yes, look at the block diagram I taught you in the previous classes. It was like this, remember? Omega n squared s squared plus omega n squared. Look at the block diagrams. It's like for the pendulum, that's right? Yes, everybody? So if I give you the closed loop transfer function, which is y over x, closed loop transfer function, first you have to go and plot this block diagram. Plus minus, this is your g open loop transfer function, y, x, unity feedback being compared. Don't forget, in the previous page I told that the closed loop transfer function is g over 1 plus g. So b over e from the previous class was g, remember? G. So you can say y over x is g generally, 1 plus g. This is equal to this example, s squared plus 1. So if you multiply the both sides from the kindergarten, 1 plus g. This to this side, this to this side. And it'll be g s squared plus 1, 1 plus g. Alright? Oh, sorry, this is g. So this g goes to hell. So the open loop transfer function, or g, is 1 over s squared. You have to put this here, as I'm going to show in the Simulink. This is 1 over s squared. Don't put the closed loop transfer function here. You have to find open loop, put it here. Understand, everybody? Yes? Do not put the closed loop transfer function. You have to find open loop, G. Here we go. G, from here, from this relation. You got it? Everybody? Yes? Okay. So this is block diagram for that. I'm going to do it in a Simulink today. I'm going to amaze you by the power of the math. Okay. Now, I'm telling you, you know what? I'm telling you the desirable input in time domain is this. Delta t minus 1. I taught you this. What does it mean mathematically? What does it mean? Look at this. What is delta? Which input to the system? Yes, impulse. I mean that I want the output of the system as a pendulum. This was pendulum, if you look at the previous notes. Follows the impulse. But this is not simple impulse. What is that? I taught you. What is that? Look at your notes. T minus 1 means what? Yeah, technical name. I told you. Look at your notes. It's starting with D. Delay. That's right. Means, as I'm going to show in the Simulink today, in the blocks and the plots, if this is delta of t and t, this is going to be like this. Means that your input signal has a delay of 1 second. So you're going to have this. Here we go. Impulse. Here is 1. Right, everybody? Huh? Original delta of t, as I defined you as input, was this. Here we go. But this is delayed. And I told you that a Laplace of any delayed function, t minus t naught, you have in your notes, is e minus t naught s f of s. You have in your notes. I'm just refreshing them. We know that f of s for the impulse is 1. I taught you. So the Laplace of impulse happens at first second, gonna be e minus s, and f of s is 1. Here we go. Why I'm doing that? Because this is your x of s. X of s. Here we go. These are s, that's right. X of s. So y of s, output of the system, gonna be x over s squared plus 1. Or e minus s divided by s squared plus 1. You got it, what, guys? Now I'm going to introduce you to new concepts today. I introduced you Laplace. Laplace function was to move from time domain to S domain. If I want to go from S domain to time domain to have the solution, you have to implement inverse Laplace. Inverse, or L minus 1. This is definition. So I want to find y of t. Y of t. I have y of s. So what I'm going to do, I'm going to apply inverse Laplace to both sides. Everybody agree? Yes? Huh? So let's go to the next page. Can I go? Okay. So I applied the delayed impulse to the pendulum, used the Laplace, made it possible, the solution, and I'm gonna now use the inverse Laplace to go to time domain. So let me write it here first. y of s was, oh my god, what happened? What's going on? Okay. Y of s was, we got e minus s, 1 plus s squared. Guys, look at here. Go to your notes. I taught you. Which function has such a Laplace? Look at your notes. In 10 cases I taught you. Which function has such a Laplace? Omega squared, s squared plus omega squared. Which function leads you to this function? Yes, sine of omega t. So when I apply inverse Laplace to find y of t in time domain, okay, so y of t is sine, but this shows me again what? I just taught you, previous page. This shows me what? Delay. So it's gonna be sine omega. So omega here is 1. That's right, 1, 1. So omega is 1. Omega, not t. T minus t naught. So t minus t naught. Huh? Sine of t minus t naught. This is your solution. Bingo. Because your omega is 1. See, omega squared, omega is 1. Interesting, right? Now let me visualize it for you guys before going to the Simulink. You applied y versus t. You applied delayed impulse to the pendulum. Here, a huge force at 1 second. Using the Laplace and inverse Laplace, it says, you know what? Your response gonna be sine start at t naught is 1. That's right. Here's, let me say is 1. Let me fix this, guys. Here's 1 because this is 1s minus 1. Your sine start at 1 second, so everything is 0. Here we go. So does the output y of t follows the input x of t? You have to use your eyes. This is x of t, this impulse. Does the output follows the input? Yes or no? Just look at your eyes. No. Yeah, exactly. So the error signal is not 0, we expect, by our eyes. So error signal, error ESS is not 0. Or ES is not 0. So, but I taught you final value theorem today. Let me examine that mathematically. So when this does happen, output doesn't follow input. I'm going to show it today in Simulink. It means you need a controller to fix that. That's why you are taking this course. You need a controller to fix this. I'm going to teach you after the midterm how to tune that. Okay, I'm going to show it today, but you don't know what I'm talking about, right? So I told you ESS is limit of x of s divided by 1 plus g. Today I just taught you. Okay, let's do that. A limit of s, x of s. X of s was delayed impulse. So here we go. This is x of s. We got it. I have to put it here, guys. It's e minus s divided by 1 plus g open loop transfer function. I don't want to see that you put here closed loop. Open loop transfer function that we found from here. I'm just writing here again. Open loop transfer function. Here also you write, also in the block diagram. Open loop transfer function. If I see that the close, you are done. If you graduate by company paying you 150K as a control engineer and put the closed loop transfer function here, you're gonna damage the product and they're gonna sue you eventually. Simple like that. This is not grading and SDSU. You get my message? Yes? So, is 1 over s squared. It's gonna be limit of s goes to 0. S cube e minus s squared plus 1. I just simplified. E to the power of 0 is 1. This is 0. 0 divided by 1, 0. Oops, this is not valid because we saw by our eyes that the error signal is not 0. As I showed you today, where is that? Error signal is input minus output. Input minus output is not 0. So it's a take-home message. Final value theory is valid for stable systems. In the first class of this semester, I told you any system oscillating forever is what kind of the system? You have your notes. It's stable or unstable or marginally stable, right? This is a marginally stable system. This is the nature of the pendulum. Unstable system gonna behave like this, goes forever. So there is no steady state value. Even here, there is no steady state value. So that's why it doesn't work. Only work for the stable system. You got it, everyone? Yes? Yes, everyone? Good. Now, before going ahead, before I go ahead, in Simulink, can I go to the next page? First, let me raise this. Okay. Okay. So, in Simulink, as I presented in the last class, or I think so, in Simulink, we do have a step function. Remember that we did together? Step function was like this. Remember the symbol? But we don't have impulse in time continuous functions. We don't have it. We don't have it. So we have to make it in Simulink, guys. If you look at your notes, guys, this is unit step in time. This is impulse. Unit step is this. Your one. This is impulse. Unknown. Remember, I introduced to you. If you look at your notes, I taught you that the time derivative of unit step is what? Impulse. This is mathematics. If you don't know, I'm presenting to you. But you have in your notes, I taught you. Because time derivative means slope at this point. Slope at this point is unknown, huge number from high school. huge number. Okay, now let me take you guys here. See, everything is simple. I told you if you apply Laplace of derivative, gives you what? Look at your notes. I specifically wrote this. Laplace of derivative means what? Look at your notes. What? When I was talking about the PID controller in your notes. Okay? This gives you what? What is this? I told you. What is this? Huh? Go to your notes. What is that? Huh? What is D? Even you cannot guess it? Do you have your notes in front of you, anyone? So I assume that nobody takes notes. Fine. So D means derivative. Derivative. That's right. So Laplace of this is S. Okay. So when I apply Laplace to the both sides, means derivative of the unit step is impulse. So it's enough that you put a derivative S after the input. It gives you impulse in Simulink. But the problem is that we don't have S even in the Simulink. It's very easy. How to make S? As remember, I introduced you transfer function in Simulink as numerator and denominator. S can be written as 1s plus 0 divided by, say, 0.1s plus 1. This 0.1 is very small compared to 1, is 1/10 of that. So the effect of this is very small. This is going to give you almost a S. So you have to write, as I'm going to show in Simulink, 1 over 1s plus 0, 0.1s plus 1. So your S is this. This is almost a derivative in Simulink. After graduation, you can use it. Even today, after developing Simulink, I'm gonna share with you. Okay, let's go for Simulink, huh? So, MATLAB. Everything is clear, guys? Yes? Huh? Good. I know that. Because S is a very noisy signal. Okay, and when I'm gonna teach you PID controller, I'm gonna tell you that never use derivative or decontroller alone because it's gonna generate noise on your system. Okay, if I want to give you a very trivial explanation, good questions. What's your name, sir? What's your name? Mike. Mike. Let me take you back to the high school. This is a graph. When I say derivative, in milliseconds, you're gonna find slopes here, that's right. See? How does it look like? How does it look like? No, lot noise. It's kind of the noise, that's right. So that's why we want to avoid the single D controller in the designing controller. Always we are using PD controllers. I'm gonna teach you. Means proportional and derivative together. See what I'm saying? Yes?
Yes. What was she
So, because I didn't teach you yet, okay?
Okay.
But if I teach you now, it's gonna confuse you, okay? So, let's go to Simulink. And, hold on. Okay. Um, mm, 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 uh, fine, project. Sorry guys, my computer is not very fast, and this version of the MATLAB is very heavy to run, so we have to wait for it. Okay, so because I already have a model previously in ME530, I'm going to change the roots here, and it's going to call what? Um, okay. Okay, so we have it. So I'm going to open the previous file that I shared with you by the email. This was sim for the pendulum problem. What I'm going to do, open one. So I'm going to just select all, Control C. Then I'm going to find the new Simulink, new, putting here. Just Control V, pasting there. Okay. Now we have the new. Okay, I'm going to save it, Control S. I'm going to share with you. I'm going to say impulse, pendulum, delay, and yeah, that's I'm gonna put it here. That's right. And error signal, because we're gonna look at it. So what I'm gonna do, there's no disturbance. Come on, save it. Okay. So there's no disturbance to the system this time, only the pendulum. What the hell is this? Okay, I'm gonna delete this. I'm gonna delete this. And I'm gonna, okay, here we go. So this is your G. I'm just writing here because I'm gonna share with you. I'm emphasizing a million times. This is open loop transfer function that we found, okay? Double click on this. It was from notes. Here we go. From notes was 1 over s squared. This is closed loop. We found from here 1 over s squared. So As I taught you, this is second order, numerator second, so it's 1. And here is S square. Here we go. See? S square, 0s, 0 constant. 0s square, 0s, number 1. Look at here, simple like that. Do you see? 1 over s square. Do you see that, everyone? Appears here? Yes? Good. So now, I told you that I want to have impulse because this is a step. Okay? Let me check the library, maybe in the new, because I'm old-fashioned professor, impulse. Do we have impulse? No, see, we have discrete time impulse, not continuous time. Okay, this is discrete time. So yes, we have to generate that. So I'm gonna copying this is transfer function, putting here between these two. Okay. Now, as I taught you, look at here. Your s is 1s plus 0, 0.1 s plus 1. I'm just exactly putting that first order system, guys. First order system. So is 1s plus 0 and see 0.1s and 1. This is going to give you the derivative. Okay, derivative. Here we go. Now, because this is delayed, here we go, guys. Here we go. See, I said that the input to the system is delayed. Input to the system is delayed. So it's very easy. This is impulse until this point. I'm just writing here. See, this is S making a step as impulse. So I want to copy and paste this here. I'm going to show it for now that this is impulse. Look at here. Oh, I'm sorry. We have to left click and connect this to this. I'm just showing for, I want to just show this, okay? I'm not changing anything. Look at here. We have double click on the scope. Hopefully it comes up. See, we have impulse. Huge, then goes to 0. What happens at time 0, guys? We want to have a delay for 1 second. You say for, I'm going to say 4 seconds. 4 seconds, whatever you want. So for that, you have to go here and type delay. Okay. Transport delay. Here we go. Dragging, putting here. And then you embed this here. So you want to delay? Good. It says that how many time delay you want to. I say, give me a number. You make a number. 2, 3, 4, 5. Which number do you want? 3. 3 seconds delay. Apply. Here we go. Now I'm gonna use this max. Look at here, guys, as we did previously. And I'm gonna put this here. Oh, yeah. See? I want to compare delayed impulse with undelayed impulse. I just want to show you step by step. Control S, I'm saving. Here we go. Look at here. This is original one, and your friend told me you have a delay for 3 seconds. Here we go. You got it, everyone? Now which that we did it, this signal, I'm writing delayed impulse. This is that what I want the pendulum that I taught you from the beginning of the semester to follow that. What does it mean? I mean that the angle of the pendulum must be 0 until here, and then has a jump and then goes to 0. But it doesn't. I showed you mathematically, right? And this is the error signal, that's right, you know that. And this is out. So if I run this output compared with the input, that's right. Here we go. As we did by mathematics, see? Oh, I have to increase the time to 25 seconds. There we go. Here we go. The blue is the input, desirable input, and the yellow is the output. And we derived by mathematics, there we go, sine t. Here was 3, that's right. You have to 1 to 3. Exactly, we derived together by Laplace and inverse Laplace. You got it, everyone? Yes? Huh? Yeah, sure. Do you know what? This is the first class that you're attending, sir? Okay, okay. So, okay. Say, sir, feedback is for compare the output with the input. Okay? So this has no relation with the G. G is for the closed loop transfer function. It relates the output over input, closed loop transfer function. This equals to, from the previous class, open loop transfer function divided by 1 plus open loop transfer function. See what I'm saying? From here, we find open loop transfer function is 1 over s squared put here. Good for asking. Again, yeah, see what I'm saying? Well, thanks for asking. Good question. Again, guys, in unity feedback or not unity feedback means we have a sensor transfer function here. Always we use open loop transfer function in the plant for G, not the closed. Closed is for whole of that. See what I'm saying? Everybody? Yes? That not you, sir. I mean that everybody. Okay. So you tell me, Payman, you taught us that this is a marginally stable system oscillating forever. Output doesn't follow input. So I'm just showing you. I'm not teaching you. Okay? I'm just showing you. After midterm, I'm gonna teach you. You are here finally for PID controller. PID controller. Don't ask me why, when, how, okay? Because it has a huge mathematics I have to teach you for at least half of the semester until it go. See, it says PID controller. When I'm double click on that, okay? And I add proportional at 1 and I don't put the integrator at 0 and derivative of at 10. Don't ask me why. Derivative s integrated 1 over s. I taught you this. Don't ask me why. I'm going to teach you. When I do that and control save this and run the Simulink block, see that magic happens. Oh, output follows input now. Input is the delayed impulse, output is a delayed impulse. See, the controller, PID controller, fixed the problem. Made system from marginally stable system to stable system. Made, look at here, bear with me. Made steady state error signal to 0. This is steady state error signal. Transient steady state to 0. And we are fine. You designed a controller after graduation for your pendulum problem. When I say pendulum problem, means I say the robot arm in the Mars. Whatever look like to that. You got it? And you're gonna tell me, Pema, why you are taught us the delayed input? Because if you want to control the Mars robotic arm from the Earth, for signal communication, there's a delay. I intentionally taught you to give you a vision, a big picture of that. You see what I'm saying, everybody? Yes? You got it? Now, because I'm going to share with you, I just wanted to show where we are going when you pass this course. I'm going to Control C. You see that if I run a game without any controller, your error signal is oscillating. There's no steady state because it's marginally stable. Error signal is oscillating between 1 and -1. Okay? And the output doesn't follow input. Crystal clear? Yes? Now, let me continue a little bit because I talked about I said in the previous case, oh, what's happening? In the previous state that the desirable input was impulse, delayed or not delayed, okay? But here I had delayed. Say your friend asked me to have a delay for 3 seconds. Now this time, I want to have, oh, this is x of t, guys. So x of t, case 2, case 1. I want to have this t minus 3. What does it this? I taught you. What is this? What is this?
Unit step.
Yes. Unit step is this. 0, 1. But this is delayed unit step. Here is 3, 2, 1. But the good news is that I don't want to solve this today, but I can share with you its Simulink file. And next class we're gonna go over it. Okay. Where is Simulink file? What I'm gonna do, I'm gonna just copy all of that, and at the same file I'm gonna put it here. See? Here we go. Okay. Here we go. What I'm gonna do, only remove this because I don't want to have this is unit step, that's right. Here we go. For again 3 seconds. Okay. Even I don't need this. Let me run it first. I want to show that it's delayed. See? This is, oh, this is from the problem of, oh, pi over 4. No, unit step. Even here, guys, you must put unit step because I copy pasted from the previous problem. This is 1 unit step. Okay. I'm running, guys. It's gonna be the same, obviously, just the scale is changing. Okay. So, and there we go. See, this is unit step 1. This is delayed 3. Here is 5. Delayed. Or we have better thing here, guys. You can even remove this because the step is here already. And you can remove all of those. Double click on this. Step time is starting at 3. It's much simpler. Okay. This is the same system. Okay. And here we go. here we go. Is it delayed at 3? This is input to blue line, and the out is yellow line, and the margin stable system. Obviously, you have error signal. You can fix it by controller. I change the input, and now you see the output is margin stable system. We're going to work on this in the next class in mathematics, Farner-Variant theorem, and eventually I want to move to the first order system, second order system, and we're going to go from there. Okay? I'm going to share the code, this Simulink model with you by email. Any questions? Huh? Guys? Any questions you may have? There we go.